Hi, hello everyone. Welcome back to my YouTube channel. As you all know, myself Kavasti, studying at Sri Venkateshwara College of Engineering at Computer Science and Engineering. Today I am going to teach about mathematics, about the topic regular stochastic matrices and their Markov chains. Let us see what is meant by regular stochastic matrices and Markov chains. Regular stochastic matrices and Markov chains are the fundamental concepts in probability and statistics with the applications in diverse fields including finance, engineering and biology. Let us see the definition of stochastic matrices. It consists of three properties like square matrix, non-negative entries and row sums equals 1. Let us see square matrix. A stochastic matrix is a square matrix whose elements represents the probability. Non-negative entries. All entries in the matrices are non-negative, representing the probabilities. Row sums equals to 1. And the sum of the rows equals to 1, reflecting the fact that probabilities of a transitions from a given state must sum equal to 1. Let us see the properties of stochastic matrices. Regular stochastic matrices, convergence and steady state distribution. Matrices. A regular stochastic matrices has a property that all of its entries are positive after the certain number of iterations. Convergence. Where raised to a sufficiently high power, a regular stochastic matrices approaches a matrix where all rows are identical. Steady state distribution. The identical rows in a convergent matrix represents the distribution of the associative Markov chain. Let us see the definition of Markov chain. It has a memoryless property and discrete time, which has also has a transition probabilities. Let us see the memoryless property. The next state depends only on the current state but not on the past state. And second is a discrete time. The system transitions between state as a discrete points in the time. Transition properties. The probabilities that govern the transitions between the states. Let us see transition probabilities and transition matrices. Transition probabilities represent the likelihood of moving from one state to the another in a stochastic process. Here Pij is denoted as, where Pij are denoted as the states. For example, P12. Here P12 represents the probability of moving from one state to the another state 2. Transition matrices. A square matrix that contains all the transition probabilities for a Markov chain. Each element Pij. Pij in the matrix represents the transition probability from state I to the state j. Rows in the matrix sum up to the 1, ensuring valid probabilities. Let us consider the Markov chain with the three states of 0.7, 0.2, 0.1, 0.3, 0.4, 0.3, 0.5, 0.3 and 0.2 is my matrices. Here in the matrix 0.7 states that the probability is staying in the state 1 and 0.2 is showing that the probability is moving from state 1 to the state 2 and 0.3 which states that the probability of moving from state 2 to the state 3. Let us stationary distribution, a probability distribution that remains unchanged over time. Steady state, the long-term behavior of a Markov chain where the system reaches an equilibrium. Let us see convergence to steady state. There are three properties of steady state. which is initial distribution, transition matrix multiplication, steady state distribution. Let us see the first property, which is initial distribution. The probability distribution of the system at the beginning is known as initial distribution. And transition matrix multiplication, repeated multiplication of an initial distribution by the transition matrix. Steady state distribution, as the number of iteration increases, the distribution converges to the steady state distribution. The applications of Markov chain. Here there are three major fields where the application of Markov chain is applied. First is a finance field, second is a networking, and third is biology. Where in the finance field we use the Markov chains in the modeling stock prices, portfolio optimization, and risk management. At the network field, we use this for analyzing the network traffic patterns, queuing systems, and routing algorithms. At the biology field, we use this for modeling genetic inheritance, population dynamics, and disease transmissions. Let us see the modeling and optimization using Markov chains. There are three major fields of state space, transition probabilities, and optimization. State space, defining all the possible states of the system. Second is a transition probabilities, determining the probabilities of the transition between the states. Optimization, finding the optimal strategies or policies to maximize rewards or minimize the costs. Let us see the conclusion and key takeaways from this Markov chain and stochastic matrices. Our regular stochastic matrices and the Markov chains provide a powerful framework for modeling and analyzing the system that evolve over the time. Their application extend across various domains, enabling us to understand and optimize complex processes. Thank you. Thank you for watching.